So we looked at vector resolution, and we've also already looked at using Pythagorean theorem to find a resultant vector. Now, we're looking through this, and we see our change. We see using our kinematic equations. So, how can we use the kinematic equations with our, just given a picture with the resultant arrow? Well, we actually take a resultant arrow. Just going to draw a quick coordinate system on here. Now, let's say our question up here is 30 meters per second north of west by 30 degrees. So first off, drawing this, north of west. So here's our west, here's our north. So we go up 30 degrees north of west. And we draw a corresponding arrow 30 meters per second. So we know that our components here are to the left and up. So we can actually use our calculator. We can use sine and cosine to find our x axes and our y axes. So we can find our x, and by the way, just a little check for later, our evaluation, our x should be negative and our y should be positive. So make sure we have that put down and we're good to go. So to find our y, we know it's sine of theta equals opposite over hypotenuse. So sine of 30 degrees times our 30 meters per second will equal our 15 meters per second upward. Then we have cosine of theta equals our adjacent over our hypotenuse. So cosine of 30 degrees times our 30 meters per second. And that's going to equal 26 meters per second. And this is actually going to be to the left. So I can also just put negative. Now, how is that helpful? Well, we can actually see that we have two components now. We did vector resolution. So we have our x-axis, which I'm just going to do in red over here. Negative 26 meters per second. And we have our y, 15 meters per second. And how does that help us? Well, say the question, this is just thinking in the question in reverse. What if our question was asking us, we have a plane flying. Here's my plane. Little engine on there, little engine on here. So we have a plane flying right there. I'm actually going to turn my plane around real fast. So we can turn our plane around. I'm going to actually fly the other way. I'm going to move it down here. We look at this. Say it's flying at negative 26 meters per second to our left. Now let's say we have a crosswind at 15 meters per second upward. And if it's at 15 meters per second upward, by the way, what would our resultant look like? So if we were on the ground, what would we see our plane do? We would see our plane fly in a diagonal at 30 meters per second. So we can actually look at that and we can find our resultants. We're finding that from our components. And all we're doing is adding it. So that was actually just a quick look of almost checking our answer from a question that asked if a plane flies to the left and it has a crosswind upward. So we start with our tail of our arrow, go to the tip of our arrow, then we go tail once again to tip. We get that right there. And what's our resultant? Our resultant is our plane flying across this way. So now that we took a look at just using our trigs and resultant vector resolution rather, and finding that resultant, now we can actually look to kinematics and using kinematics to find what we're doing and find that resultant vector. So how can we do that? Say we have a ball or a projectile launched at 20 meters per second to the right. I'm also just going to have east on here. From a height of 20 meters. Our question is, how far does our projectile or ball go in the horizontal direction? So what we're actually looking for, so I'm just going to write our guesser down. Our givens, 20 meters per second equals our VI. What else are we given? Oh, we always know A from now on is going to equal negative 9.81 meters per second squared. We have that as our A as well. We know our change in our Y direction equals 20 meters. So now, what are we looking for? Well, our unknown, we don't know our time it takes to fall and hit the ground. That's a question mark. We also don't know how far that it goes. We don't know our change in X. And I'm even going to draw a picture for myself, so I'm going to draw it right over here. Let's just say here's a table, or cliff rather, because it's 20 meters. And our ball starts on top of it. So our ball starts up here. It's going this way. 20 meters per second. Now it's going to come off of here until our ball hits the ground down here. Now we don't know this. Change in X. We do know our Y. This is 20 meters. Our time is a question. And A equals negative 9.81 meters per second squared. So we have all of that. Now if we ignore air resistance, by the way, we're going to ignore air resistance. What can we see? What do we need to know? Well, we see that our time I'm going to go back to our blue. For our equation, we can find our time it takes to fall because our ball is just getting launched horizontally. So this is where we can look at our X and Y positions. So with our ball, since our arrow is directly to the right, our X component directly to the right, but our Y component, is it up? Is it down? No. We don't have a Y component. It's all in the X direction. So I could even have a little sub X here. I'll just draw that in black, it'll be easier to see. Have sub X right there. We have our vi sub y equaling 0 meters per second. So we can find how far it would go before it hits the ground. Because if we think back to, or even think towards the firing of a bullet, or also the dropping of a bullet, they hit the ground at the same time. And they hit the ground at the same time because the x and y components are separated. So if we look at our equation here, I'm going to go back to blue, and we see we have change in x, or change in y in this case. We have vi, we have an acceleration, we have a time. So our change in y is going to equal vi in the y direction times t plus 1/2 at squared. Now we know that our y direction, this is just 0, it goes away. So change in y times 2 divided by a, all of this square rooted, that's going to equal our time. So if we plug that in there, we get 20 meters times 2 divided by negative 9.81 meters per second squared. By the way, time would be square rooted. This be a negative under the square root. I actually need to put a negative 20 there, so I need to come back up here. These are all negative 20 because it's downward 20. So if we see that, that equals our time. If I plug that into our calculator real fast, what do I get? I see that it's 40 divided by 9.81, all square rooted. I get about 2 seconds. It's like 2.02, but that's okay. So 2 seconds for our time. So now we look at this and we have our time. And once we have our time, we can actually find out how far it went. Because if we think about it, gravity's just acting straight downward. So our horizontal, assuming no air resistance, never changes. So if it doesn't ever change, it's always going to be continuously going at 20 meters per second to the right, even though it is going down now. So we can look at our distance traveled to the right, or in our east direction, as just a continuous 20 meters per second, even though our resultant would be a diagonal. I'm actually going to take this, I'm going to make it a little bit smaller and move it upward. And our guesser's still there. I'm just making it so I have room. Okay. Now, if we look at this, we can look at what equation are we going to need next. By this, that would have been solved. So our second equation we would need is the same one. Now we have change in x equals vi t plus 1/2 at squared. We plug in our t into here. What do we get? We get change in x equals 20 meters per second times 2 seconds plus 1/2 times, what's our a, by the way? Our a is 0. So this just goes away. Our a is 0 because our acceleration due to gravity is just downward. It's not to the right or left. And that's where breaking up into components and using vector resolution helps out significantly. So we can see our change in x is 40 meters. So there you go. There's your answer. And that's how you get it. When we evaluate the results, it better be positive. It's to the right. Good. By the way, you write these down for evaluating results. There's our solve. Or evaluating results, you'll write this sentence out. But it's going to be positive. It's going to be 40 meters to the right, which if you think about it, is falling pretty far, but it's also going off there pretty far too. So 40 meters seems reasonable to me. And we're still using guesser as the year goes on, but that's how you're going to use kinematics to figure out projectiles falling off an edge. we can also take a look at a different problem dealing with an angle. So this is when we're thinking about our projectile launching. And what do we need to do with our projectile launching? Well, we need to use vector resolution first. So let's say our launcher, in this case, is 20 degrees of elevation. So I'm going to draw my coordinate plane right here. So 20 degrees of elevation would be that. Now what else would 20 degrees of elevation, or what would it look like? Well, let's say it's getting launched at 7 meters per second. Just a marble launcher. So we draw our arrow at 20 degrees, and this is 7 meters per second. And then we know from here, we can use trig to figure out our x, because it's going to be moving to the right. We can also use trig to figure out our y, moving upward. So when we look at this, our y component of our initial velocity is going to be our opposite, so sine. So that will equal sine of 20 degrees times 7 meters per second, while our vi sub x is going to equal cosine of 20 degrees times 7 meters per second. And the way I got those, by the way, are equations for that. Remember, sine of theta equals opposite over hypotenuse. Cosine of theta equals adjacent over hypotenuse. So we're using that, and we're finding our x and y component. Now, why might that be important? Well, from that picture right in there, I'm even going to draw acceleration on here. So our acceleration is going to be downward. And what does that mean for our final distance? Now, once again, we're looking for horizontal distance. So if we're looking for that horizontal distance that it's going to travel, we have to take into account that it started with an initial velocity upward. And why do we have to take that into account? Well, it doesn't change our distance it goes to the right, per se, but it does change the distance, or the time, rather, that it stays in the air. So now, instead of our vi being 0 for our change in x, or in this case, change in y, by the way, we're still saying it's a 20. We won't even say 20. I'm going to say 0.2 meter fall. Just off of a little stand, a couple books. So 20 centimeters. So our change in y is going to equal our vi sub y times t plus 1/2 a t squared. Where this a is still negative 8.1 meters per second, but this v is a positive velocity. And that's going to change our time. So we're just going to still run through these calculations. I'm not going to finish it on here, but that's how you would set it up. And that would change what you're doing for the problem. And we're actually going to be looking forward to these problems with our lab. And with our lab, we can see where a projectile is going to launch. So being able to break them up with vector resolution, being able to use Pythagorean theorem to figure out our resultant vector can help us check those questions. But it all works together in unison to be able to figure out how far a little marble is going to fly through the air and how far it's going to land on a target. So, yeah.